This is 5.4. We're going to continue our knowledge of logarithms. There are 3 formulas that you need to know. Okay. The first formula is called the product rule. Second formula is the quotient rule. And the third is the change of base formula. Each of these is very, very simple. So let's start with the product rule. If I had x to the third and I multiplied it by x to the fifth, if the bases match, what am I allowed to do with the exponents? Add them. Everybody understand that? Okay. What if this was a y? What can I do with the exponents? Nothing. The bases have to match. If the bases match and you're multiplying, then you add the exponents. Okay. What if I had y to the fifth over y to the seventh? If the bases match, what do I do with the exponents? Subtract. Okay. And that leads us to the product and the quotient rule. So if I have log base A of 7, let's do 7x. So here I have base A of 7x. That is exactly the same thing as log base A of 7 plus log base A of x. So anytime you have a logarithm with 2 numbers multiplying each other, and I should probably put this in parentheses, because the logarithm is an exponent, you can take those two and you can add 2 different logarithms to each other. Likewise, if you have 2 logarithms where the bases match, then you can multiply the 7 and the x together and put it into a single logarithm. So sometimes you want to take a small logarithm and separate it. Sometimes you want to take a big logarithm and condense it. Okay. Well, the quotient rule says log base A of 7 over x is equivalent to log base A of 7 minus log base A of x. Pretty simple. Okay, and then I'll get to the change of base formula. Oh, sorry, I said there were 3. There are actually 4. The third one is the power rule. And the power rule says if I have log base A of 7 squared, that is exactly the same thing as 2 log base A of 7. So if you have an exponent inside your logarithm, you can drop that exponent out front. Or if you have a number in the front of your logarithm, you can bump that up to become an exponent. Let's see some of these in action. Excuse me. Let's do this one. Oh, that's kind of complicated. Let's do an easier one. All right. So number A, log base 8 of 11 minus log base 8 of 7. Can I put those together? Do the bases match? Yes. And we're doing a positive logarithm minus a logarithm. What is the answer going to be? Log base 8 of 11 over 7. Okay. So the next problem, log base 5 of something plus log base 5 of 8 is equal to log base 5 of 24. 3. Why 3? 3 times 8 is 24. Okay? So the negative 4 log base 6 of 3 is equal to log base 6 of, so this is the power rule. I can take the negative 4 and stick it up front, up top, and I get 3 to the negative 4. What is 3 to the negative 4? 3 times 3 is 9, times 3, 27, times 3, 81. What does the negative do? Flips it upside down, so this would be 1 over 81. So in general, positive logarithms land in the numerator, negative logarithms land in the denominator, and the power rule allows you to move that coefficient to the exponent. Okay, let's do a couple more of these. Log base 7 of 2 minus log base 7 of 5 is equal to log base 7 of 2/5. The log base 7 of 2 is positive. That's positive. So the 2 goes on top. This is negative, so the 5 goes in the denominator. Okay? Log base 9 of 10 plus log base 9 of something is equal to log base 9 of 70. It's got to be a 7, because 10 times 7 is 70. All right? Log base 7 of 81 is equal to something times the log base 7 of 3. What would this be in base 3? Would be 4, 3 to the 4th. So 81 is 3 to the 4th, and we drop that 4 down, and we get 4 log base 7 of 3. Do you guys want to see another set? Think you got that? Okay, let's make it a little bit harder. Okay, here I have log base z, log with no base, of z to the 9th times x. Now, if your logarithm has no base, it's because we're lazy. Just like we're lazy when we write that. What does that symbol mean? Square root. So what number is resting inside there? 2. Why don't we write it? Because we're lazy. Mathematicians are very, very lazy. And square roots are more common than third roots or fourth roots or fifth roots. And so those are just, that is the common square root, and there's a 2 in there. We're just too lazy to write it. We do the same thing with logarithms. If a logarithm has no base, then it's base 10. And that's called the common log. Any logarithm with no base is base 10. Now, there's another logarithm where you don't write the base, but we'll get to that later. So, excuse me. How do we expand this? So we're going to write this in 2 logarithms. What are they going to be? Log of, and there is a 10 on each of those. We don't need to write it though. Z to the 9th plus log base 10 of x. Can we do anything else to this? No exponents. How do we fix that problem? We drop the 9 out front. So 9 log of z plus the log of x. And that is considered expanded. Okay, let's look at another one. I have got frogs all over in my throats today. Okay. What is the expanded form of this? Log y to the 4th. Then what? Minus log of x. Should I go any further? Drop the 4. So 4 log y minus log x. Everybody good with that? Do you want to see another one? Yeah? Okay. This will be log z plus 5 log y. Log z plus 5 log y. Any questions? Okay. All right, how are we going to put this together? So we have a positive logarithm and a positive logarithm. The bases match, but in order to put those together, I need to turn these into exponents. So I'm going to put the 6 up here, and I'm going to put the 1/2 up there. Combined, they will be log base 6 of 4w plus 1 to the 6th over w plus 7 to the 1/2. And let's see, it might want you to use the square root. Let's take a look. Oh, hey, somebody stop me. What did I do wrong? Yeah. Oh, man, that's embarrassing. So I took that as a negative. If that was a negative, then you would divide them, but it wasn't a negative, so you should multiply. Feel free to tell me, hey, Mr. White, you're dumb. It won't hurt my feelings. I already know that. There we go. Does that make sense? Do you want to see another one? All right. Okay, this is a good one. I'm going to bump the 1/2 up here. I'm going to bump the 7 up here. And I have 2 positive logarithms and a negative, and they all have the same base, so I can put them together. This will be log base b of z to the 1/2 y to the 7th divided by x. Positive logarithms land in the numerator, negative logarithms land in the denominator. Okay. All right, last formula, the change of base formula. The change of base formula is kind of weird. Whoa, that's new. So when we're driving the logarithm bus, there are an infinite number of gears and they all work differently. So in your calculator, you would need an infinite number of buttons to solve logarithms. And it turns out you don't need all of the buttons. You only need one, and in fact you have 2. So the change of base formula says if you have log base 7 of 5, and that's going to be some irrational number, that is exactly the same as log base a of 5 divided by the log base a of 7. Yeah. So imagine on your calculator the number 5 was broken. You didn't have a 5. Could you still do all the math you needed to? How would you get around that? You would just put parentheses 2 plus 3 every time you were supposed to use a 5. Okay? Well, we can kind of do the same thing with logarithms. If we don't have 7th gear, If you're driving the log bus and you go to shift into 7th and there is no 7th gear, that's okay. It turns out you can drive in any gear you want. And the formula to change the gears, to change the base, is you take the log of any base you want of 5 and you divide it by the log of any base you want of 7. Excuse me, guys. So, if you look at your calculators, we have a log button. And if we push log, it doesn't tell us the base, which means it's base 10. So if I wanted to do the log base 7 of 5, I do not have a button that is base 7. I do have a button that's base 10. So I'm just going to type in the log of 5 divided by the log of 7. So log 5, close the not good. Log 5, close the parentheses, divided by log 7. And the answer is 0.82. So now let's go back to our original question. What is log base 3 of 21? How would I solve that? Log 21 divided by log 3. And what was the answer again? 2.771, and then we gave up. Well, now it will spit out all the decimals. 2.771, 2, 3, 4, 7, 4, 9, and it keeps going. Okay? So logarithms allow us to solve unknown exponents. So the question is, how did the calculator get that number? Well, it's more complicated than you think. There actually is no simple way to solve for exponents. Okay? Yes, we created logarithms, and that allows us to get the answers, but before calculators, how did they get this? And the answer is they published logarithm textbooks. And this is no joke. A big, fat textbook. This actually would be a pretty small one. And this textbook has lots of chapters. It has chapter 2, which is log base 2. So if you want log base 2 of 7.5, you'd open to chapter 2, and all it is full of little tiny numbers arranged in columns. And you would read chapter 2 until you got to 7.5 or whatever you're doing. You say, oh, the answer is this. And that is literally how they solved logarithm problems before. They would carry around textbooks that had all the answers. I saw one my last year at BYU. I saw a logarithm textbook that obviously they don't print them anymore. Okay, well, what if your textbook doesn't have chapter 529? Well, then you just go to chapter 10. So if the question is, what is log base 529 of 17? Well, my textbook doesn't go up to 529. But I do have chapter 10 or any other chapter. So I would do log base 10 of 17 divided by log base 10 of 529. And it turns out all you need is one chapter. If you have chapter 10, that's all you need. Everything else can be computed using chapter 10. So I would go to chapter 10 and I would do the log of 17. And then I would go to chapter 10 and do the log of 529 and divide those two, and I get the answer as 0.45. Okay, so really we are guessing and checking. We're just doing it in an easier way. So instead of guessing, they used to have textbooks, and you just kept scrolling down through the decimals until you found the answer you wanted. But now we have developed a formula that can estimate the logarithm, and that's kind of complicated. It's way beyond the scope of this class. But that's how the change of base formula works. So the last problem in ALEKS simply says, use the change of base formula to compute log base 5 of 1/3. So we do the log of 1/3, make sure you close the parentheses, divided by the log of 5. And the answer is negative 0.68. Okay, that's it for 5.4. Get to work.